Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss some problems on Module 3 in Analog and Digital Communications course. Analog and Digital Communications course. So already 2 modules are covered, now in 3rd module. So the 3rd module belongs to the Analog and Digital Pulse Modulations. Okay, so analog and pulse modulations. So in this module we are going to solve some problems. Okay, so module 3 is covered by course outcome 3. The 3rd course outcome states illustrate the concept of pulse modulation schemes, demodulation, sampling, quantization, and coding for obtaining of digital data. So from this module we are entering into the digital data. Why? Because this is analog and digital communications. First 2 modules is completely analog communication, that is amplitude modulation and angle modulation, but here onwards we are entering into the digital data. Okay, so that's why we are going to solve problems on digital. Okay, so here in question bank we are discussing only the part A, that is a problem solving and critical thinking questions. So in problem solving critical thinking questions, we are using formulas and you go to apply, and some critical thinking is also needs to solve these problems. Okay. Now the first problem is find the Nyquist rate and the Nyquist interval for the following signals. G of t is equal to sync 200t and B bit is G of t is equal to sync square 200t, and third bit is G of t is equal to sync 200t plus sync square 200t. Okay. So for this, the first one, the sync pulse corresponds to a bandwidth of W is equal to 100 Hz. So hence the Nyquist rate is 200 Hz. So we know that Nyquist rate Fs greater than equal to 2Fm or 2W, what it may be. So the Nyquist interval is 1 by 200 seconds. So this is Nyquist interval. One is the Nyquist rate, another is the Nyquist interval. So Ts is 1 by 200 seconds. And coming to the second bit, this signal. What is the second signal? Second signal is sync square 200t. Sync square 200t. So sync square 200t as a product of sync pulse of sync 200t with itself. Since multiplication in the time domain corresponds to a convolution frequency domain, so we find that signal G of t has a bandwidth equal to twice that of the sync pulse 200 sync 200t. So there is a 200 Hz. So the Nyquist is double, so 400 Hz. So Nyquist interval is 1 by 400 seconds. Okay. Coming to the last one. The bandwidth of G of t is determined by the highest frequency content of either sync 200t or sync square 200t. So from earlier parts, sync square 200t has the higher bandwidth equal to 200 Hz. Okay, so this is a sync square. One is a sync 200T and one is a sync square 200T. So sync square 200 is the higher bandwidth, which is equal to 200. So this supports. So correspondingly, the Nyquist interval is 200 into is 400, and the Nyquist interval is 1 by 400 seconds. So Fs greater than equal to 2W. My W is 200. So Fs greater than equal to 2 into 200, it gives 400. So the Nyquist rate is 400 and Nyquist interval, which is equal to 1 by Fs, to 1 by 400 seconds. So by using calc you can solve this one, but it's enough. Coming to the second one, 4 channels, 2 with a bitrate of 200 kbps and 2 with a bitrate of 150 kbps are to be multiplexed using multiple slots TDM with no synchronization bits. So 4 channels, 2 with a bitrate of 200 kbps and another is with 150 kbps. Now answer the following. What is that one? Assume 4 bits from the first 2 sources and 3 bits from the second 2 sources. Calculate the size of frame, frame rate, duration of a frame and data rate. Okay, so the solution is, so first one is the frame carries 4 bits from each of the first 2 sources and 3 bits from each of the second 2 sources. So 4 into 2 plus 3 into 2. Okay, totally having 4 channels. Okay, totally having 4 channels. First 2 channels with 4 bits and another 2 channels with 3 bits. So the frame size is 4 into 2, 8 plus 3 into 6, 14 bits. So this is a frame size. So each frame carries 4 bits from each 200 kbps. So are 3 bits from each 150 kbps. Why? Because out of 4, 2 with 200 kbps and remaining 2 is 150 kbps. Okay. So the frame rate is 2 lakh by 4. 2 lakh by 4. That is 2 lakh by 4, which is equal to 150,000 by 3. So finally it is 50,000 frames per second. Okay. Now frame duration, that is equal to 1 by frame rate. Already we have the frame rate is 1 by frame rate is 50,000. So frame duration is 1 by 50,000. So it is 20 microsecond. And dbit is output data rate. Output data rate. So output data rate is 50,000 into 14 bits per frame. So here in denominator frames is cancelled. So bits per second. So how much bits? 700 kbps. So the data rate is 700 kbps. So we can also find the we can also calculate the output data rate as a sum of input data rates, because there are no synchronization bits. There is no synchronization bits. So output data rate is equal to 2 into 200 plus 2 into 150. So that is data rate. Why? Because 200 kbps, 150 kbps. So totally 4 channels. 2 is 200 kbps and remaining 2 is 150 kbps. So 2 into 2, 400 plus 2 into 300, 700. So 400 plus 300 is 700 kbps. Okay. So third problem, 3 signals M1, M2 and M3 are to be multiplexed. M1 and M2 have a 50 kHz bandwidth and M3 has a 10 kHz bandwidth. So design a commutator switching system so that each signal is sampled its Nyquist rate. Okay. So three signals M1, M2 and M3 or multiplex. So first two is 50 kilo, remaining is 10 kilo. So here M1 and M2 both having 50 kilo. So what is the Nyquist rate? 100 kilo. So that means Fs is greater than equal to 2 Fm. So 2 into 50, 100. So 100 kilohertz is equal to here 1 lakh samples per second. So similarly, M2 also same. Fm is 50 kilo. So Nyquist rate is 100 kilohertz. Whereas M3 is 10 kilo. So 2 into 10, 20 kilo. So 20,000 samples per second. So now we are going to design a commutator switch. So what is the output rate of a commutator? So 1 lakh plus 40,000. So 2 lakh 40,000. Okay, 2 lakh 40,000. So how many channels are there here? This 240 divided by 4. So that is the 60,000 per rotation. M1, M2, M3. Okay. So take in a TDM BM signal with 2,40,000 samples. So 2,40,000 divided by 4 is 60,000 rotations per second. 60,000 rotations. So that is the speed. Now the fourth one, for a PAM transmission of voice signal with W is equal to 3 kHz, calculate transmission bandwidth if Fs is equal to 8 kHz and tau equal to 0.1 ds. Okay. So Ts is equal to 1 by Fs. So Fs is the sampling rate, you can say. So our Nyquist rate. So Nyquist interval is 1 by Nyquist rate. So 1 by Fs. So 1 by 8 kilo. So my Ts is 125 microsecond. So what is it tau? Tau is 0.1 Ts. So 0.1 into 125 micro. So it gives 12.5 microsecond. So here I required bandwidth, transmission bandwidth. So the bandwidth is greater than equal to 1 by 2 pi. 1 by 2 tau. 1 by 2 tau. So the bandwidth greater than equal to 40 kilohertz. Bandwidth is equal to 40 kilohertz. Now, fifth one, 4 messages band limited to W, W, 2W and 3W respectively are to be multiplexed using TDM. The minimum bandwidth required for the transmission of this TDM signal. So in this problem, 4 messages or 4 channels are to be multiplexed using TDM, time division multiplex, having the bandwidths W, 2W and 3W. Okay. So what is the minimum bandwidth required for the transmission of this TDM signal? Okay. So during sampling, we sample at 2W. Why? W is the given. So sampling is F is greater than 2W. So sampling 2W. So with this rate of signal of bandwidth, we get sampled properly. So signal bandwidth 2W is sampled properly, is being fed twice in the commutator switch. Okay. So, and the bandwidth 3W is fed thrice into the commutator switch in order to get a sample at an effective rate of 6W. So here Fs must be greater than equal to 2W. So in this way we are going to add all this. First one is W. So it is 2W, again W, 2W, and 2W, that is 4W, and 3W, it is 6W. So totally 14W. So the total bitrate is 14W. So the minimum bandwidth is RB by 2. RB by 2, minimum bandwidth. So 14W divided by 2. So you got 7W. So very simple problems. Next one is a sinusoidal signal of amplitude A is quantized by a uniform quantizer. Assume that the signal utilizes all the represent levels of the quantizer. If the signal to quantization noise ratio is 31.8 dB, find the number of levels in the quantizer. Find the number of levels in the quantizer. Okay. So here you are going to find L value, number of levels. So the reference levels is represented as L. Okay. So in a PCM system with a sinusoidal input, the signal is given by 6N plus 1.8 dB. Okay. So this is the standard formula for output SNR in dB. Or simply you can say SNR output dB is equal to 6N plus 6N plus 1.8 dB. So L equal to 2 power N. L equal to 2 power N. So here we go to find the L value. So by using this formula, 6N plus 1.8 equal to 31.8 dB. So from this 6N equal to 31 point minus 1.8. So what you get? 30 dB. So all this in dBs. So N equal to 5. So N equal to 5 bits. So L equal to 2 power N. So 32 levels are required. 32 levels. Okay. 32 quantization levels or 32 representation levels are required. Seventh one. A message signal M of t is transmitted by binary PCM. Let the signal to quantization noise SNRQ required being at least 47 dB. Determine the minimum number of quantization levels L required and SNR, assuming that M of t is sinusoidal. Okay. So here also using the same formula, L equal to 2 power N. L is the representation levels or quantization levels, that is equal to 2 power N. N is the number of bits to represent. Okay. And another formula is S by NQ. So signal to quantization noise ratio, dB is output signal to quantization noise ratio in dB is equal to 1.76 plus 20 log L. So this is the formula. Okay. But here also go to find L value. So S by NQ output dB is equal to 1.76 plus 6.02 N. So given 47. So 47 equal to 1.76 plus 6.02 N. So we are move this 47 move this 1.76 towards 47, so it goes to minus, and finally go to solve. N value is 7.5 and approximately equal to 8. Okay, so substituting this 8 value, 1.76 into 6.08, we got 49.9 dB. So this is in dB. So this is SNR output in dBs. Okay. And eighth one, find the maximum amplitude of a 1 kHz sinusoidal signal input to a delta modulator that will prevent slope overload when the sampling rate is 10,000 samples per second and the step size is 0.1. Okay, so delta is a step size, that is equal to 0.1. Find the maximum amplitude. So the step size is required to avoid the slope overload error. So that the slope of m of t, message signal, slope of the m of t less than equal to step size into sampling frequency. Okay. So AM is the amplitude of the message signal. Omega m is the message angular frequency, less than equal to step size by TS or step size into Fs. Okay. So substituting all the values, that is Fm. So here omega m is equal to 2 pi Fm. So you go to substitute. Fm is 1 kilo, less than equal to Fs 1 into 10 to the power 4 into 0.1, that is the step size. So after solving this all values, you get AM is 1 by 2 pi, and again you go to substitute as pi value 3.14, 1 by say 6.24, you get the AM value also. Okay. So ninth one, signal M1 is band limited to 5 kHz and 3 other signals M2, M3, M4 each band limited to 4 kHz or time multiplexed and fed to a PCM encoder having M equal to 1024 quantization levels. Find the bitrate of PCM and also minimum theoretical bandwidth for transmission. Okay. So totally 4 band limit signals are used to multiplex through a PCM encoder, and the encoder having levels 1024. Here M is used, but generally L value we are using. Okay. Yeah. Here FM1 is 5 kilo, FM2 and FM3, FM4 are 4 kHz. L value is 1024. Okay. So first messaging frequency is 5 kHz. Second, third and fourth having 4 kHz. So what is the bandwidth formula? RB by 2. Okay. L equal to 2 power n. So here my L value is 1024, which is equal to 2 power n. So 2 power 10 is equal to 2 power n. So my n equal to 10. Why? Because here you go to find the bandwidth. For finding bandwidth, we require the RB, bitrate. So how to get the bitrate? That is from NFS. So n, number of bits is represent or required for finding the RB. So bitrate is equal to NFS. Fs equal to 2FM. So you got to find the RB1. Why? 4. We're having 4 message signals or 4 channels. Okay, so these 4 channels are multiplexing. So first you go to find the RB1, NFS, N is 10, FS 2 FM. Okay, this is N, this whole is the 2 FM. So RB equal to NFS. So 10 into 10 into 1000. So we get finally the 100 kbps, 100 kilobits per second. That is RB1. And remaining 3 are same. So we go to find 1 and multiplied with 3. That's enough. Okay. So RB2, here also n bits, n is a 10 and 2 FM, 2 into AF, 4 kilo. Okay. So it is 80 kbps. So RB2 value is 80 kbps. But first one is only 5 kilo, remaining 3 are 4 kilo. So the total bit rate is equal to RB1 plus 3 into RB. Why? Because here the remaining 3 channels are having the same rate. You find that is RB2 is 80 kbps. So 100 plus 3 into 80. So 380 is a 240 plus this 100. So finally 340 kbps. So this is my RBS. So what is the bandwidth formula? RB by 2. So 340 by 2, we got 170 kilohertz. So this is my bandwidth, the required bandwidth, okay, for that system. And the last one is for a DM system, the signal sampled at 76 kilohertz, A max is equal to 4 and Y signal bandwidth is 3.5 kilohertz. Assuming that the signal is sinusoidal, determine the output signal power, SNR, and transmission bandwidth. Okay. So here you go to avoiding the slope overload. So this is the condition. Delta by TS greater than maximum slope of the message signal. So this is the maximum slope of the message signal. Delta is the step size. Okay. So the condition to avoid slope overload is A less than equal to delta by 2 pi FM TS. So delta minimum step size to avoid the slope overload. Okay. So you go to cross multiply, that is A into 2 pi FM divided by Fs. Why? Because Fs is inversely proportional to the time period. Okay. So 2 pi FM into A max, maximum amplitude, okay, divided by Fs. So what is FM? FM is 3.5, A max is 4, Fs is 76 kilo. So this is Fs 76 kilo, this is 3.5 is FM and maximum amplitude is 4. So finally we got 1.4 volts. So that is the minimum step size is required to avoid the slope overload. Why? Because this is one of the drawback, the slope overload. So we must avoid this slope overload. Okay. And the quantization noise power for DM is NQ. We represent this quantization power is NQ, delta square by 3. Already we got delta. So delta square by 3. We got 0.7 watts. This is the quantization noise power. So the voice bandwidth is only 3.5 kHz. So the normalized quantization noise power at the received output is N dash Q, that is equal to NQ into FM by FS. Okay, so NQ already find 0.7 into FM by FS. So FM we know 3.5 divided by FS. So finally the normalized quantized noise power is 32.2 milliwatt. So this one is the normalized quantization noise power. So the output signal power is A square max by 2. So A square, A max is 4. So 4 into 4, 16 divided by 2, 8. So the output signal power. So S naught is 8 divided by normalized quantization noise power you find. So substitute this 32.2 milli. So finally the output signal power is 248 watts. 248 watts. Okay. So for developing of this content using Simon Hacking, J.S. Chitodi, Sanjay Sharma, and many other books, Haribot like that. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.